Hey there, welcome back to Real Analysis. In this section 2.5, we're going to look at some examples and develop some terminology for when a sequence doesn't converge, when a sequence doesn't have a limit. So we'll give a formal definition of this down here in a second, but when a sequence doesn't converge, we say that it diverges. So this section is called divergence. Okay, so let's start off reminding ourselves of the main kind of what we call the epsilon n definition of limit or convergence and also some notation. So if we have a sequence Sn, let's remember what we mean by it converges. It converges to some number, a real number L. And well, what does the definition say? It says if for every positive number epsilon, you can calculate some natural number, some capital N, so that when your index, your sequence input, a little n exceeds that capital N, the distance between S sub n and L is less than epsilon. All right, and the two pieces of notation that we use for that, they're interchangeable. We can write this kind of calculus-looking notation. The limit as n goes to infinity of Sn equals L. Or more briefly, we'll just write Sn arrow L, and then you can omit it if you want, but you can also include this if it helps clarify it. We mean that, and you read this out loud. Sn approaches L as n approaches infinity. So you read the arrow as approaches. All right, so that's our kind of main definition from last time, section 2.4. So if we negate that definition, let's try to write down what we mean if a sequence doesn't have a limit equal to L. All right. So I'm just going to negate the definition that was written above. If the limit as n goes to infinity of Sn is not L, then what does that mean? That would mean that there has to exist some epsilon, right? The negation of for every is there exists. And then what would be true about that epsilon? Well, it would have to be true that no matter how you pick capital N, so for every capital N, you can always find some index bigger than it, and the distance between Sn and L is greater than or equal to epsilon. All right. So I would encourage you to kind of stop the video and kind of verify that I've correctly negated my quantifiers. I'll kind of, say in the definition that the limit equals L is there for every epsilon. So I say there exists an epsilon. And then in the definition, it would be there exists some n. So the negation of that is for every n. And then here, instead of saying for every n greater than or equal to n, there has to be one where the condition isn't true. So that's kind of confusing as I say it out loud, I guess, here. But that's what we mean by the the limit as n goes to infinity of Sn not being the number L. Okay. So we're going to use this terminology that Sn diverges if no matter how you pick the L, the limit of Sn is not L. So that's kind of the analog of the limit notation. I just put a line through the approaches arrow. Sn does not approach L. Okay. Let's look at an example. I'm going to define this sequence Sn as follows. It has two values. The sequence terms are 0 when the index n is even, and they're 1 when n is odd. All right, so if you wrote this sequence out as a list, it would have the values 0, or sorry, starting with n equal 1. It would start with 1, 0, 1, 0, 1, 0, and so on. I think it's intuitively clear that sequence does not have a limit. It is not the case that its terms are going to get close to some value as n goes to infinity because they keep alternating back and forth between 0 and 1. So let's see if I can't use that definition that we wrote above carefully, or the negation of the limit definition, to prove that. Let's try to prove that this sequence diverges. It's going to be a proof by contradiction. Suppose there is some number L in the real numbers that this sequence approaches. Okay, well then for any epsilon, in particular, if I take epsilon equal, to a half, then I should be able to find some index value that the sequence terms differ from my limit by less than a half, provided my index, the index value is bigger than that. All right. So that's just using the negated, that's just using the definition of convergence. Okay, but now I'm just going to look at kind of what those terms look like. If that n is greater than or equal to capital N and it's an even number, which it certainly is possible that it's even, well, then this difference Sn minus L is 0 minus L because the sequence terms are 0 when n is even, and that difference has to be less than a half. Using properties of absolute values, I can write that like that. Then my limit is somewhere between minus a half and a half. But kind of proceeding along the same way, if you take an n bigger than that cutoff value, capital N, and it's odd, which again, these n's exist, then the difference between Sn and L in that case is 1 minus L, right? So that's less than a half. So that tells me that 1 minus L is less than or equal to, or sorry, greater than or equal to minus a half and less than a half. So if you add those two things together, if you add the inequality that I'm underlining in blue here to this one, then you get this kind of ridiculous inequality, right? Because minus a half plus minus a half is 0. L plus 1 minus L is 1, and a half plus a half is 1. So adding those inequalities together gives me the fact that 1 is less than 1, and that's not true. So there's our contradiction. So this sequence, in fact, does not have a limit. And when a sequence doesn't have a limit, we say it diverges. Nice. Pause the video and soak that in. I'm just going to move on to the next example. Okay, so let's consider this sequence, the sequence whose terms are the square root of n. As n goes to infinity, the square root is an increasing function, right? As n gets bigger, its square root gets bigger. So intuitively, it clearly diverges. And if you open up your calculus book, you could probably find a statement in there written something like this, that this limit is equal to infinity. Yeah, and we want to use such notation as well, but I just want to emphasize here in our careful real analysis course that such a statement, the limit as n goes to infinity of the square root of n equals infinity, isn't defined, and it's not defined because infinity is not a real number. Let me write that in the notes. The symbol infinity is not a real number. So we can only write the limits symbol here when something approaches some real number L. All right. So the following definition is how we're going to be able to kind of justify this. We have to expand, if you like, our terminology. So here's how we're going to do it. Definition 2.9, if you're given some sequence Sn of real numbers, we're going to say it diverges to infinity. I'm not going to say it converges, because converges means that the limit exists and equals a real number, and infinity is not a real number. But this is kind of just a very specific kind of divergence. So it diverges to infinity is the term that I'm defining. The notation I'm going to use to write that down is like what was written above. The limit is infinity, or we can just use the arrow notation. So Sn approaches infinity. And then what does it mean? It means for every real number m, so there's our first universal quantifier, no matter how you pick the real number m, then there's an existential quantifier. There exists some number n, right? So you have to kind of carefully use these things when you're proving stuff. And that, what does that have to happen? There exists some number n that the sequence terms are greater than or equal to m, provided the index is greater than or equal to capital N. All right. So if we write that in kind of the chalkboard symbols, what are we saying? We're saying that it diverges to infinity if for every number m, there exists some number capital N, it's an integer. Here I didn't, let me kind of be a little bit more precise here and say for every real number m, there exists some integer, natural number capital N, such that I'm going to write it as, I'm going to write Sn is greater than or equal to capital M for all n greater than or equal to capital N. Okay, so there's the sort of quantified statement with chalkboard, and so you can kind of write your own negation of that statement. Maybe it's going to be useful to know what it means to not diverge to infinity. I want to make a little remark here. I'm going to squeeze it in. I've got something written down here, but I'm just going to squeeze in a little remark here that this is one of my favorite acronyms. I'm going to say it out loud and just write it. Without loss of generality, or WOLOG. It's kind of a funny acronym because I'm writing without as WO, but without loss of generality. So what I mean by that is that it doesn't hurt to make this assumption. You're not changing the nature of any argument, that without loss of generality, the number m is positive. right? Because if that statement above is true for all m, then in particular it's true for all positive m. And that's the spirit of it. The spirit of a sequence diverging to infinity is that its terms are getting big. So getting big in the sense that they're eventually bigger than any positive number. So whenever I'm using this definition, I'll always make that assumption. So I'll try to make it clear when I do, but if I don't, I always implicitly mean it. Let's look at an example. All right. Let's prove our claim that we had above. I claim that the limit is the sequence square root of n diverges to infinity. Yeah. So that's just another way of saying this limit statement. The sequence square root of n diverges to infinity. How to prove it? Well, let's use our brand new definition. Take a real number, m, and like I just said, let's assume it's positive. Okay, and I'm kind of skipping the discussion part of the proof, but I would maybe recommend you try to stop the video right now and see if you can't work out the discussion part of the proof yourself. But here I'm just going to kind of go forward with the proof. I'm going to use the Archimedean principle to say that I can always find a natural number that's greater than or equal to m squared. Why did I get that m squared? Well, it came from my discussion that I'm omitting from you guys here in this video. But it's certainly true that given a positive number m, I can find a natural number that's bigger than its square. So then if you take little n bigger than that n, then little n would be bigger than or equal to m squared by the transitivity of greater than or equal to, right? Then those are positive quantities, m squared and n. So you can always take the square root of both sides of an inequality. So taking the square root of both sides, I get that the square root of n is greater than or equal to m. So what have I done at the end of the day? I've shown that for any positive number m, I can find some number such that if my index is greater than or equal to it, my sequence terms are greater than or equal to m, and that is by definition the statement that the square root of n diverges to infinity. Nice. Right, so the spirit of it is diverging to infinity means that eventually the terms of the sequence will be larger than any pre-specified value. The pre-specified value is the number m. Let's do one more. I'm going to try to keep this lecture a little bit short. This time I am going to include kind of the discussion section. So I'm going to take a sequence here whose terms are this rational function in n, a cubic polynomial over a quadratic polynomial, n cubed plus 1 over n squared plus 1, and I claim that that goes to infinity. I'm certain that you've probably seen such things in your calculus course, yeah, that when a rational function's degree of its numerator exceeds the degree of its denominator, then as the input goes to positive infinity, so does the output. Calculus students learn this stuff, but they don't kind of prove it rigorously. Here, let me try to prove it rigorously. This time, I'm going to kind of include you on the backstory. So I want to have not a formal proof right now, but kind of working out, because what do I have to do? That's what I've written in the beginning of the discussion. Given some number m, and again, without loss of generality, I'm going to assume this number is positive. Given some number m, what do I have to do? I have to show that eventually, that is for large enough values of little n, my sequence terms are greater than or equal to m. So that eventually, I'll usually use this phrase for sufficiently large n. So what do I mean by that? I mean for little n greater than or equal to something, capital N, and we need to find that capital N. We need to say like, well, how large is sufficiently large? It depends on capital M. All right, so doing a little bit of algebra, I omitted the kind of nitty gritty details here. I don't want to do polynomial long division in front of you, but that's how I did this. Using polynomial long division, I divided n cubed plus 1 by n squared plus 1, and I got a quotient, n minus 1, a linear term, and I got a remainder, 2. And so I can write that that fraction is the quotient plus 2 over the same denominator. Right, so that's with polynomial long division. And then I'm just going to do a little bit of arithmetic. I'm taking this 1 and rewriting it as n squared plus 1 over itself. That's it. And then what am I going to do? This next step maybe needs a little bit of explaining. That term that I've highlighted in green, that term is greater than or equal to 0. Let me write it over here in a different color, kind of parenthetically. N squared plus 1 over n squared plus 1 is a positive number for all natural numbers n. Yeah, it's 1. It's equal to 1. I just confused myself. 1 second here. Oh, I'm getting a little bit ahead of myself. Sorry. I'm not going to edit this video. Now you're seeing my raw material here. I got a little bit ahead of myself. First of all, why did I get that common denominator? I got that common denominator so I could combine those two fractions. Sorry about that. So you guys check that if you take those two fractions whose denominators are n squared plus 1 and combine them, well, what do you got? Negative n squared minus 1 plus 2. So here's your negative n squared, and here's your plus 1. Sorry about that. And now it's this term that I was going to focus on. That term, 1 over n squared plus 1 is positive. Pardon me. 1 over n squared plus 1 is a positive number for all n. So if I omit it from this expression, yeah, there's three things here, and I'm just going to omit it. So omitting a positive number that comes with the sign plus in front of it would make the quantity smaller. So that's kind of a typical idea that we'll use a lot in these inequality arguments, that if you have a bunch of things added together, so, and in particular, the sign in front of one of your positive terms is addition. If you just omit that term, well, you don't have equal anymore, but you did make the result smaller. Okay, so moving ahead, sorry about my blunder here. Now I'm looking at this thing, the remaining two terms. Remember, I'm trying to make this expression greater than or equal to this m. So I'm looking at this quantity over here, n squared over n squared plus 1, and I note that it's less than 1. For any n, because the numerator of that fraction is less than the denominator, that quantity is less than 1. Okay, so if I pick n a little bit bigger, if I pick it bigger than m plus 1, then that difference I have, I'm just replacing this n with m plus 1, making the result smaller. Yeah, but then I would know that that is greater than m because, again, this difference, 1 minus n over n squared plus 1, is positive. Yeah, it's positive because when you're subtracting something from 1 that's less than 1, the result is positive. Omitting a positive term makes the result smaller. Cool. So now I kind of see how to condition. I see how to choose my capital N. M plus 1 might not be a natural number, but that's no big deal. I can always find a natural number bigger than it. All right, stop the video, see if you can kind of absorb those steps, and then we can finish this video just by writing the formal proof. All of the necessary pieces have been put into place. So here's just a header. I just want to prove this statement. So here's my formal proof. Start by letting m be any real number, and without loss of generality, choose it to be positive. Okay, then use the Archimedean principle to pick a natural number that's at least as big as m plus 1. Okay, then if you choose an index value bigger than that, I'm just going to recapitulate that algebra that I did above. Let me try to do it more carefully this time. My sequence terms, after a little bit of polynomial long division and algebra, are given by that expression. If you read the example in the book, the author just kind of throws this at you, but now you kind of see why. There's a couple steps in there, but it was with polynomial long division and then doing a little bit of algebra. And then, like I explained, if I omit a term that's greater than 0, I make my expression smaller. Yeah, but I've said that n is greater than or equal to n, which is greater than or equal to m plus 1. So I can replace this n with m plus 1, making the result even smaller. And then the last step is, well, because n over n squared plus 1 is a number that's less than 1, 1 minus it is positive. So if you omit it, you make the result even smaller. So at the end of the day, what have we shown? We've shown that this quantity, As long as you take n sufficiently large is greater than or equal to m was an arbitrary positive number, and so by definition, we've shown that that thing diverges to infinity. All right, so I hope this was helpful, and I would strongly encourage you to look at the author's example in the book. It's a slightly different, but not too different, and then kind of fill in all the details. Get out a piece of paper and sort of put in every detail that you need to understand that kind of terse argument that the author wrote in the book. Well, thanks for listening.